Hello students. In last sessions of the chemical reactions of alkenes, as we know that alkenes normally undergo ionic electrophilic additions reactions. Likewise, addition of dihydrogen, addition of halogens, additions of halogen halides, and now we switch over to the another additions of H2SO4. So in this case, addition of H2SO4, as we know that sometimes is called as an indirect hydrations of alkenes too. So in this indirect hydration, the indirect hydrations means we have to add water not in a direct manner but indirect manner. So in these reactions we have to take a cold concentrated sulfuric acid. This is cold and concentrated H2SO4 added to alkene, okay, to form a alkyl hydrogen sulfate. This is alkyl hydrogen sulfate. What is in these reactions? I think so we particularly focus on the mechanisms too. So in these reactions, first these pi electrons, they are the electron source, and H plus is electrophile. So definitely first step, these electrophiles attract towards to this pi electron. Okay, so we get a first step is like that, H plus which can be added here, and remaining portion plus is connected with O minus SO2 OH. So this is ethyl hydrogen sulfate. In case particularly we know that this alkene is a symmetric in nature, but if we have a propene, right, this is propene is a asymmetric alkene. When addition of this, as we know that this H2SO4 is an unsymmetric reagent, is not a likewise H2 or X2, right, is near about is HX or HOX or water likewise. So definitely they follow the Markovnikov rule. What is the Markovnikov rule that we have to understand in our last sessions? The additions of unsymmetrical reagents, right? Additions of unsymmetrical reagents such as HX, H2O, HOX, this H2SO4 to unsymmetric alkenes occurs in such a way that the negative part, particularly this is the negative part, okay, of the adding molecule goes to the carbon of atom of the double bond, which carries lesser number of hydrogen atom. Here only one hydrogen, two hydrogen. So these minus portions which can be attached towards to the this particularly portions. So we get a product is like that, and it's called as an isopropyl hydrogen sulfate. But this additions is due to Markovnikov additions because secondary carbocation is more stable than the primary carbocation. Now, what is the mechanism behind it? It's an easy mechanism. Now you have a certain idea about the mechanism. When electrophilic additions reactions occur, at that time, first step from the pi electron resources, they attracts this electrophile H plus. It's a very slow step because there is a cleavage of bond, so it's require energy, so it's a slow step, it's a rate determining step, and in these particular reactions we observe that there is a electrophilic addition reactions. That's why the name of these reactions is known as electrophilic addition reactions. We get a product is like that, CH3 CH plus CH3 is isopropyl carbocation. There are one more possibilities if this pi bond is shifted to here. So this is minus and plus, so we get like that CH3 CH minus and CH3 plus, but it's a primary carbocation. As we know that secondary carbocation is more stable than primary carbocation. What's the reason behind that? In the case of carbocation, they are less stable, highly active, but due to hyperconjugation as well as inductive effect, secondary carbocation is more stable. So according to this secondary carbocation now is attached with this O minus SO3. It's a nucleophilic attack. As we know that all nucleophilic attack because it's a clear cut plus and minus that can be seen. So the rate of reaction is fast. So it's not a rate determining step. So we get a product is like that, isopropyl hydrogen sulfate. So this is about the additions of sulphuric acid. But what does the title suggest that? Why it's called as an indirect hydration of alkene? What is the importance of these reactions? This alkyl hydrogen sulfate on boiling with water, so they undergo hydrolysis and to produce alcohol. So the preparations of alcohol from alkene with the help of this cold and concentrated H2SO4. So in nutshell, or in a 2-in-1 step, we particularly give the example is like that. Thus alkene can be converted into alcohols. For example, if I am having a ethene, first step is you have to add concentrated H2SO4, cold concentrated H2SO4. So it's converted into ethyl hydrogen sulfate, and the further hydrolysis with a boiled water is converted into alcohol. So this overall two-step conversions of an alkene first into alkyl hydrogen sulfate and followed by the hydrolysis with a boiling water to form an alcohol is called as an indirect hydrations of alcohol. So this is about the addition of H2SO4. The same process, but it's a different title. Now we move to the additions of water. What is the meaning of addition of water? We have to add water, but direct hydrations of alkene. In last case, first we have to add H2SO4 and then followed by boiled water. So it's an indirect hydrations of alkene, while in this case we have to add direct water. So what's the difference between them? Because by hydration, the meaning of hydrations means we have to add a water. Ordinarily, water does not add directly to the most of the alkenes. If you add a water into alkene, because this water is a highly polar in nature and alkene is non-polar in nature, so it's not possible, right? So at that time, some reactive alkenes do add water in presence of mineral acids like HCl, H2SO4 to form a alcohol. Fine. So the additions occur here. The same, particularly it's a symmetric or asymmetric. Definitely it's a asymmetric because carbon double bond carbon. Here this carbon is attached with 2 hydrogen, while in this case it's connected with 2 methyl. So it's a different in nature. So it's called as an asymmetric alkene. So when asymmetric alkene when reacts with a asymmetric reagents like water, at that time we have to follow the Markovnikov rule. What's the negative portion? OH. How less number of hydrogen here, because there is a 0 hydrogen, so the OH is connected with this carbon and hydrogen is connected with this carbon, so we get a major product as a tertiary butyl alcohol. These reactions, which can be explained with the help of Markovnikov addition, when Markovnikov additions is used when your particularly alkene is asymmetric and your reagent is also asymmetric in nature, right? What is the mechanism? It's a simple mechanism, as we know that it's an electrophilic addition reaction. Mind well, at presently our main topic is the electrophilic addition reaction. So in this electrophilic addition reaction, CH3C double bond CH2, okay, when H plus in water or in acid, particularly in case of acid, it's not from water, okay, it's from acid. So acid is an electrophile, and this electrophile here, pi cloud, which can be attracted towards to this electrophile, is the first step, slow step. So we get a tertiary carbocation, highly stable in nature. And this tertiary carbocation now, because it's a nucleophilic attack. But this nucleophilic attack, why it's a nucleophile? Because it's a Lewis base. So O is having an electron pair, so it's a Lewis base. So this connected with this carbon, and we get a product is like that. It's an intermediate product, and thus further oxygen is more electronegative. So they pull electron from this bonded electron pair between O and H, and we get a product is like that. So it's a simple mechanism that we have to understand, because it's an electrophilic additions reactions. First step, pi electrons of the double bond cloud attacks to the electrophile H plus to form a carbocation, and as we know that this carbocation is readily reacts with the water and to form a alcohol. Okay, so this is all about the electrophilic additions reactions. As we know that when we start when we start chemical properties of alkene, so first is a popularity or it's a dominant nature of alkene is to give electrophilic additions reactions. But students having some questions, so only gives this type of no. Some reagents also added by a free radical mechanism. Under special conditions, alkene also undergo a free radical substitutions reactions. But besides that, alkene undergoes oxidation reactions, ozonolysis reactions, and polymerizations reactions. Okay, these particular reactions we briefly described as below. Now the main point, number 2 point. First one is the electrophilic additions reactions. Now we oxidations reactions of alkene. Oxidation reactions of alkene. So alkenes undergo a number of oxidation reactions to give a different product, because it's based on your alkene is symmetric in nature or asymmetric in nature, your alkene is terminal in nature or a-terminal in or non-terminal in nature, your particularly oxidizing agent is weak in nature or high in nature, right? So various conditions which can be applied to the oxidations reactions of alkenes. So first is the complete oxidations with oxygen or air, sometimes called as combustion reactions. As we know that any type of hydrocarbon, right, any type of hydrocarbons when burns in oxygen or air to form always CO2, H2O, and this process is called as combustion reactions. All combustion reactions, as we know that they are highly exothermic in nature. For example, ethene when reacts with oxygen, full amount of oxygen is used, so it's a complete oxidation, gives CO2, H2O, and this combustion enthalpy is near about 1411. So this amount of energy is released when ethene is complete oxidized with oxygen. So this is about the complete oxidations reactions. Now another topic is like that. Now we switch over to the another topic is a controlled oxidation, right? It's a controlled oxidation. What is the meaning of controlled oxidation? So controlled means we have to regulate the supply of oxygen either with the help of a special type of reagents. So in controlled alkenes reacts with a number of oxidizing agent to give a different product. So first the oxidation with potassium permanganate. So different products are also formed depending upon the reactions conditions. So first I use a dilute KMnO4. Mind well, cold and dilute. Once again, this KMnO4, this MnO4 is cold as well as dilute, right? In neutral or alkaline conditions. As we know that because of the presence of pi bond in alkene, there is a presence of pi bond in alkene. They are readily oxidized by cold and dilute neutral or alkaline KMnO4 solutions to give a vicinal alcohol. Vicinal means two hydroxyl group are joined with two different neighboring carbon. It's called as vicinal, right? So, or 1,2-diols, or sometimes called as 1,2-glycol 2. The name of this compound, PET name is ethylene glycol. IUPAC nomenclature of this particular compound is ethane 1,2-diol. So itself reduce and the KMnO4 itself reduce into what? MnO2. These reactions is sometimes called as hydroxylation reactions. These reactions is sometimes called as hydroxylation reactions. In this process, two hydroxyl groups are added across the double bond. Simple manner, two hydroxyl groups are added across the double bond. So it's a simple reactions. Once again, here you having a cold and dilute KMnO4. As we know that the oxidation state of manganese in this case is +7, is converted into what? +4. So it means KMnO4 is reduced. So they gain electron. It means that they oxidize opposite compound like ethene. Okay. So when in presence of H2O is converted into KOH, MnO2, and this is called as a nascent oxygen. It's a freshly prepared oxygen. It's called as a nascent oxygen. And this nascent oxygen, when reacts with this ethene and at a normal temperature, we get a hydroxylation reactions. Same way, for example, if I having a compound like that, so this is the example of what? This is the example of ethene. Now we switch over to the propene. When propene is same way reacted with dilute KMnO4 at 25 degrees centigrade temperature, so therefore from KMnO4 dilute we get a H2O and nascent oxygen, and this nascent oxygen is hydroxylated at a double bond position, so we get a 1,2-diol or sometimes it's called as an vicinal or 1,2-diols or 1,2-glycols 2. So we get a product propane 1,2-diol. This is also reaction is called as an hydroxylation reactions. In these reactions, the pink color of KMnO4, because the color of KMnO4 is a pink in nature, right? This is pink in nature. Okay, KMnO4 solution is discharged and a brown precipitate of MnO2 is obtained. So the color of this particular is brown in nature. So it's a one type of a test for unsaturation. Likewise, in the case of bromine, when we have to use a bromine, so at that time the brown color of bromine which can be discharged into a colorless. Same scenario that we have to observe in these reactions too. So these reactions is sometimes firstly given by a Bayer. So it's called as an Bayer's test. In this test, Bayer's test, so is a test for unsaturations. So this is about the oxidations with a dilute. Now we switch over to the oxidations with hot KMnO4. It's a cold, while this one is hot in nature. So the condition is different. So when an alkene is heated with hot KMnO4 solution, cleavage of C double bond C occurs, leading the formations of carboxylic acids. Here it's end up to alcohol, but here the oxidation is extended up to carboxylic acid, right? Sometimes they give the ketones as well as carbon dioxides depending upon the nature of the alkene. For example, I having these two types of alkene. As we know that in this alkene, it's a terminal alkene. Yes. What is the meaning of terminal alkene? In alkene in which double bond are present at the end of carbon chain are respectively called terminal alkenes. In this case, in the terminal, but it's a non-terminal. Why? Because double bond is not particularly located at the end of the carbon chains. So they are non-terminal alkynes. So in two cases with terminal alkenes, one of the product is always when you have hot KMnO4 oxidized with a terminal alkene, your one product is mandatory formic acid. And formic acid having a lower oxidation state, so is further oxidized because this hot KMnO4 is also oxidized this methanoic acid into what? Into CO2 and H2O, right? So this is about the ethene. Now we connected with the CH3 double bond CH2. It's a terminal alkene. It's the same terminal alkene. When it reacts with a nascent oxygen, KMnO4 KOH 100 to 110 degree centigrade temperature. As we know that any case of terminal alkene firstly gave the product formic acid. The oxidation state of formic acid is too low, so it's converted into CO2 and H2O, and we get a product here from this 2-methyl propene is acetone. The name of this particular compound is acetone. Now, what case that we have to observe in a non-terminal alkene? This is non-terminal alkene because double bond is not end of the chain. So in case of non-terminal alkenes, carboxylic acid, either your product is carboxylic acid or your product ketones or both carboxylic acid as well as ketone, which can be depending upon the nature of the alkene. For example, if I having an example in your book is butene. So when butene is oxidized, so they oxidize or the particularly cleavage, okay. So the cleavage of the C double bond C is format which can be converted into carboxylic acid CH3COH. Same way here Ca3CH2COOH and Ca3COOH. So two different products. But in this case, Ca3C double bond O, Ca3C double bond O. So we get a 2 mole of acetone. So this is about the non-terminal alkene. One more particularly portions is like that. One more portions is that can be discussed in our next portion is called as an oxidations with ozone. It's an interesting portions that we have to study it in our next session. Thank you very much.